Okay. So first thing is you should have the test review on Blackboard. The answers are also there now, but remember the test is Monday. And what I'll probably do, assuming I messed up the one this morning, so we'll see if I can make it correct Monday, is I'll make it available at something like 10:20. I think I said this already, and then give you until something like 11:50. So an hour and a half. That way, if I mess up, there's a bit of leeway. If you have trouble uploading, there's a little leeway. And most of these assignment things you can still submit it, even if it's late. It'll just have a little late tag next to it, and I'll just ignore that, of course, if there's a problem. Now I'm curious. Can you? I just got beep. Did you hear beeps? Yes. Okay. So yeah, those are when someone submits the test. So you'll be hearing those every once in a while. Sorry about that. So today is kind of a typical thing, which is we went through a decent amount of stuff on Monday, and now we go back and we do a bunch of examples. So let's start with 4.3. Start with a basic one. Sorry. The final, it will in general be at the same time, but similar to the tests, we'll probably give you a bit of extra time so you can go in a little bit early, and you will have a little time at extra time at the end. And if you are in a different time zone, at some point I'll send out an email asking if you are, and we'd set it up so that you could take it at a different time if there's a problem. So the final is at the regular time for most of you. So this first one is kind of the reminder of what we're getting from this section. So here you're given an F by this, and you're given a curve that goes from 0, 0 to 3, 4 along a line segment, and then from 3, 4 to negative 1, 7 along a line segment, and then from negative 1, 7 to 1, pi along a line segment. The submission should end fairly soon, but still a few minutes. So remember, this section says if something is conservative, then we don't care about the paths. All we care about is where we start and where we end. And since this is the definition of conservative, which is capital the vector field is conservative if it's the gradient of a given f. So that says it's conservative, and that says that therefore I don't care about the paths. All I need is to plug in the two endpoints into that potential function. And so it doesn't come out to anything nice, but if I put in 1 pi, I get x e to the negative 1 plus pi natural log of 2. If I put in 0, 0, everything's 0. Look at that. So in this one, this question is kind of the basic one, just saying, well, if it's conservative, well, this is defined to be conservative, then we don't care about the path. So they've kind of on purpose made it a fairly involved path because we can then just ignore it. So there's the base idea in 4.3. So any questions on this? Oh, that should be a 1. Thank you. So e to the negative 1. So here, obvious. Whatever that number is. So any question on this? This is the idea. So we don't have to parameterize. We don't care about the path at all. So now let me go to one where you have to do a bit more work than this, but similar idea. Here there's a preliminary question, and for some reason they broke this up into 2 pieces. In 9, you're given this vector field and you're asked if it's conservative, and then in 17, you're given a curve and asked to get the line integral on the curve. So 9 and 17 really go together. So how do I check to see if something is conservative? In this one, it's 2 variables, so it's an easier one. So how do I check to see if this is conservative? And just so you can more easily answer, let me call that P and that Q. So what has to be true for it to be conservative? So you need the derivative of P with respect to Y is equal to the derivative of Q with respect to X. The second derivatives, the mixed derivatives, are the same. So here, P of Y is equal to 2y plus 6xy squared. Qx is equal to 2y plus 6xy squared. So that's okay. Because remember, for it to be conservative, this should be the gradient of something. So therefore, in that case, the first term would be the derivative with respect to x, and the second would be the derivative with respect to y. So if we make a second derivative, so py would be, if it's conservative, fxy, and qx would be fyx, which would be the same. So it is conservative. So therefore, let's find the potential function. And how do I do that? Actually, let me start because it's hard to write the symbols. F, we would assume, is the derivative with respect to x, which means that f would be the derivative, the antiderivative of p with respect to x. And so the antiderivative of p with respect to x and remember we get the usual plus c, but the c now could contain the variable y. So we might be missing something. So what else is f equal to? Have to be equal to? Has to be the integral, has to be equal to the antiderivative of q with respect to y. Right? Again, we might be getting the other variable. In this case, they're exactly the same thing, so we don't get anything new. And therefore, now I can make it just a regular plus c. So here's the base idea. We'll do another one with 3 variables after this one. But the idea is we take the antiderivative with respect to both, and anything that is in one or both of them will be in the actual function. So we should expect repetitions. Sorry. We should expect repetitions, just don't write them twice. So any questions on this part? And then we'll go to 17 to follow up. Okay. So 17 is for the vector function we started with, the vector field we started with. And it says, here's our path. And so here again, they give the path. It goes from -1 to -1, 0 to +1, 0 along the circular radius 1 centered at the origin. Then goes from 1, 0 to 1, 1 along a line segment, and then goes from 1, 1 to -1, 0 along a line segment. So as with 2, they made this a fairly elaborate one. But in this case, it ends up being really easy. What is the integral in this case? 0, because since we start and end at the same point, it's a closed curve, and conservative, it's the function at the original point minus the function at the end point, but those are the same, so they cancel. So here I didn't have to remember the one we got from 9. So if it's conservative and it's a closed curve, then the integral will be 0. The line integral will be 0. Okay. So any questions on this? Okay, so only go to 3 variable one. Pretty much do the same thing as this problem. So here's our vector function. Is this conservative? So now 3 variables. And that last one, minus y sine of z plus e to z. So in some ways, this is an extension. Again, if it is conservative, then this is the gradient of some function f. And again, we need all the mixed second derivatives to be equal by giving labels. It would mean I would need that, just like the last one, I need q of x equals p of y. I need r equals p of z. I need r of y equals q of z. Or you can use the curl, which you can remember as, this is the memorization technique, but you shouldn't need this for the test. Because it's a memorization technique, and for the test, you can just write it down. So to be conservative, we need all the second derivatives to be equal. And that's the same thing as saying that the curl needs to be the 0. So we go through all the pieces. So the derivative of r with respect to y is negative sine of z. The derivative of q with respect to z is also negative sine of z. Derivative of p with respect to z is 0. Derivative of r with respect to x is 0. Derivative of q with respect to x is cosine of y. And derivative of p with respect to y is also cosine of y. Therefore, you get everything cancels. It's the 0 vector, 0, 0, 0. Therefore, it is conservative. So similar thing, just more of it. And so in theory, if we had 4 variables, we could do the same type of thing. Again, we'd need all the second derivatives to be equal. Obviously, we're not going to make you do that because that would be, that's 12 comparisons. Wait, or choose 2. So 6 comparisons. But we wouldn't make you do that. And now let's find the actual function. And this again is an extension of what we did in the last one, which is now we can assume that this actually is the gradient of some function f. So I'm not writing this down because I'm trying to keep it all in one piece of paper. So in terms of the first one, what is f in terms of p? It's the antiderivative with respect to x. Yep. And so the antiderivative of p with respect to x is x sine of y. And now, now we might be missing 2 variables. F is also equal to the integral of q with respect to y, which is x sine of y plus y cosine of z. And again, we might be missing 2 of the variables. And it's also equal to antiderivative of r with respect to z And again, we might be missing two of the variables. So all those are f. And now we just put it all together. And plus a regular constant. So this one we gain one new one every one we took. So again, don't write anything twice because it's just repeating it, because it is the same function. So any questions on this? So there probably is a follow-up one, I forget if there is or not, where you're then given a curve, but now it's the same thing. If I want to do the line integral over some c of this vector field f at the top, then I would just look at the endpoints and plug those endpoints into my potential function at the bottom there. So any questions on this? Okay, so those are the ones I might look at in 4.3. Any questions on this? Any questions on other ones from 4.3? Okay, so 4.4 is again still doing line integrals for a different case. So let me do a couple of those examples. So here's a vector field. So 4.4 is Green's theorem, right? Which I'll write once we actually use it here. So, and something I'll remind you. So our path is a circle of radius 1. We know from 4.2 it doesn't, if we have a closed curve, it doesn't matter where we start. So I don't have to tell you where we start. And here we're going around the circle clockwise. And again, I want to do the line integral of the function over c. So the first little quick thing you would do is, since it's a closed curve, you will probably want to quickly check if it is conservative, because if it's conservative, we know the integral is going to be 0. But here, is this conservative? And so remember what we do is we check the derivative of p with respect to y, which is 2y. Derivative of q with respect to x is 2y but plus 5. So they're not the same, so this is not conservative. So actually, are going to have to do something a bit more. On the other hand, it is a closed curve. So here's our picture. And we are going clockwise. So we want to find integral of c, this. And Green's theorem says if the path is closed, that this is equal to the double integral over the region R of q of x minus p of y, dy dx, dx dy, which are, or whatever it's going to work out to be. So this is the main thing in 4.4, which is if we have a line integral and the path is closed, instead of doing the regular line integral where we have to parameterize the curve, what we can do is look at the double integral over the closed region of qx minus py. And here, I started saying it, so q of x is equal to y plus 5. P of y is 2y. And here I'm missing a little something. So let me add in here. Is it assumes we're going counterclockwise, which means when I go back down to here, I have to put a negative in front because we're going the opposite way. So you have to be a little bit careful here that you're going in the correct way. And then once we get here, I don't actually have to do the integral because since that's a constant, what is the integral? I'll bring the negative 5 out. What's the double integral of 1? Oh, I think in the original one it was a circle of radius 2, but that's okay. So I changed the problem a little bit. So what is the area? No, so if you have a constant, if you do a double integral over a region, it gives you the area of the region. And the area of this circle is, of course, pi r squared, where r is 1, so we get that. And you can see, so here it's not conservative, so the technique from the last section doesn't work. And you really don't want to do it from 4.2 because we would parameterize it where we would let x be the cosine t and y be the sine t, and then we'd have to switch it so that it goes backwards, and then we have to plug it in and then take the derivative and take the dot product, and so we'd be getting things like e to the cosine t, which would be a real mess. So the negative again is, so here's the added bit, which is the Green's theorem assumes it's counterclockwise. So since here it is clockwise, we're going the opposite way, so we're doing the negative work. So here's kind of the base for 4.4. This is Green's theorem, which is if it's closed, then you can change the line integral into a regular double integral over the closed region of q of x minus p of y. So any questions on this? And in some ways, this is fairly typical, which is we often make you really want to use Green's theorem because, for example, here, q of x minus py is just a constant, so we don't actually even have to do the integral. Whereas you put in these extraneous functions, making it so if you actually do it using the parameterization, it's going to be really messy. So that's fairly typical. Okay, so another one. So here again is a vector field. And instead of writing what C is, I'm just going to draw it. So it is going from the origin to the point 1 over square root of 2, 1 over square root of 2, and going along in the counterclockwise direction, the circle of radius 1, start at the origin, and then going from 0, 1 along the line to back to the origin. And we want to find, if this is C, I'm not sure why it's making my 3's look like weird things. That's x to the 5th minus y cubed, x cubed minus y to the 5th. So again, it's closed. So again, we want to at least quickly check, is this conservative? Nope, because the derivative of q back to x, I'll again label them, is 3x squared. Derivative of p with respect to y is minus 3y squared. That doesn't work. So it's not conservative, which means we don't want to do it. Green's theorem says, well, but we can make this into a double integral over the enclosed region of q of x minus p of y. So we get a regular double integral. So go back to 3 point, I forget where we did double integrals, 3.2 or something like that. So how do I do this double integral? So unlike the last one, we actually have variables, so we actually have to do the integral. But how do I do this? Am I going to use rectangular or polar? Yeah. So you can see, again, they made it so this is nice, which is since it's x squared plus y squared inside the integral, that's going to become nice. And our region is an arc of the circle. So 3x squared plus 3 squared will become 3r squared. We'll get the usual extra r. R goes from, in the actual problem, they reminded you that it was a circle of radius 1. Here I just drew it, so it's 0 to 1. And theta goes from, what angle is this? Pretty obviously goes up to pi over 2 and pi over 4. It's supposed to be pi over 4. And here, unless you really want me to, I'll do my usual thing, which is, you can see this is a pretty easy integral. It's just 3r cubed. So we could get this as a number, but I'm going to stop there unless you want me to actually do it. It's just 3/4, 3/4 times pi over 4. Okay, so another one. It's a closed path, therefore we can use Green's theorem, and in this case it works. So actually, no, I do want to get this, so I think, yeah, so I'm lying. I am going to do this because I'm going to use this in the follow-up. Sorry about that. So any questions on this one? As I said at the beginning of both these two problems, you should be at least checking to see if it's conservative, because Green's theorem assumes we have a closed path, and if it's conservative with a closed path, then the integral is just 0. So conservative in some ways is the easiest. So not a bad idea to check. A little thing is, notice here, this pretty much assumes we're doing two variables, because otherwise we'd be getting a three-dimensional thing, and we don't do that. So Green's theorem is pretty much 2 dimensions. So any questions on this? So as I said, let me do the sort of follow-up. So for the same f as in 9, but now C is not the closed curve, it's just the first two pieces. And again, I want to get this. And so the idea is, well, I can see that that last one, let's call this C3, is a fairly easy line, because it's going along, I should put in the, this is 0, 1. It's going from 1 to 0, 0, therefore x is 0, so it's going to be a pretty simple parameterization. So why don't I use what I had in the last one? So I do C prime is equal to C1 plus C2 plus C3. We know from the last one that that is 3 pi over 16. And we know that the integral of C prime is equal to C plus C3, which says that the integral over C prime is equal to the integral over C plus the integral over C3, and therefore the integral over C is equal to integral over C prime minus integral over C3. So if it isn't closed, if it is simpler than doing all the pieces, which here might very well might not be, that's not a very complicated path. But if it was a more complicated path, it might be easier to close it, get it on the missing piece, and then subtract. So for C3, we're going to have to do the actual 4.2 method, which is we have the line from zero, 1 to 0, 0. And we want to parameterize. So obviously x is equal to 0. And then here's where you can have lots of possible answers. So first one is what we did on Monday is I just said to get the line, just do the chapter 1 method, which is subtract the end from the start. So that would be 0, negative 1. And then do xy is equal to 0, 1 plus t times negative 1. And so we get y is equal to 1 minus t. I'm instead going to do this. And the only little thing is it gets atypical, which is in that case, we'd go from 1 to 0 in the integral. And the reason is I'm going to be putting this into something where I'm going to be cubing it. And so I don't really want to have 1 minus t. So this will be easier to cube. But you don't have to. So we get our usual thing. Plug that into our function. which was the x to the 5th minus y cubed. So put in y equals t and x equals 0. Again, put in y equals t and x equals 0 and y equals t. Take the derivative of the parameterization. Notice in the I know that the derivative of the parameterization is going to be 0 comma something. So I really don't need this first entry because I know when I take the dot product, I'm going to get 0, which will come up when we'll actually do when we get more complicated stuff. So we get the integral from 1 to 0. Not sure I'm putting negative, that's just plain 1. And so I get, looking at my notes, I messed up. So negative 1/6. Oh yeah, thank you. My notes are right. Plus, and therefore, trying to keep it all on one page. Oops. Is equal to the integral over C prime, the full closed path, minus what we just got. So I said in this one, it might not make sense. It might have just made sense to do C1 and C2 and then add them up separately using the 4.2 method because there are only 2 pieces. But it might not be because the path C2 means we're going to start getting things like sine and cosines cubed into the 5th. We probably don't really want stuff like that. So the usual thing again is if we want you to use Green's theorem to do most of it, the pieces that we want to look at are kind of annoying if you try them directly. Whereas the piece that you're adding in is a fairly simple one. So any questions on this? All right, so those are a couple from 4.4 I will look at. Any other ones from 4.4 that you have questions on? I should say before I move forward, so now we'll start quickly, do the usual quick intro into the next topic, 4.5 in this case, but pretty obviously, since tomorrow's review, so we're not going to do anything new, pretty obviously it's not going to be on the test. So I'll do the usual quick introduction of 10-15 minutes, and then we'll ignore it until next Wednesday, because again, test is on Monday. Okay, so quick intro. So here we're going to look through flux or just flow through a surface. So given a velocity vector field at V flowing through some three-dimensional region, so now we're doing 3 dimensions, we want to know the flow through a 2-dimensional region M. And this will be called the flux through M. And if you want to think of something, think of a river. And the way the river is moving at all the different points would be the vector field V. And you can think of M as kind of an invisible net, which is a 2-dimensional object that you're putting into the river. And we want to know how much water flows through that region. And that's the flux. So a definition. So given the 2-dimensional region in 3 space, each point on M will have 2 normal vectors, just whatever the vector is and the one in the opposite direction. We will pick one of those 2. To be the orientation, so either flowing upstream or downstream, for example. If we can pick orientations at each point continuously, which I'll say in a second, the surface is orientable. And in some ways, to get an idea of what that means, let me look at an example where this isn't true, which is a surface that is not orientable is the Mobius strip. So, question, does anyone know what the Mobius strip is? Yeah, so Mobius strip is take a region, twist it, and then attach the ends. And if you do that, if you follow along on one side, follow a path all the way to the other end, you'll find that you end up on the opposite side. And so if we tried putting orientations everywhere as we went along, we'd find, oh, it switched. And therefore, that is not orientable. So orientable just means that as you're going along, you don't have any discontinuities where something flips, like it does on the Mobius strip. So the usual thing, it's fairly nice. And almost everything is going to be orientable. Okay. Since we're looking for the flow through M, and I'll just choose randomly that we'll use n instead of negative n. And parallel to n, we do the usual physics thing, which is we only care about the part of v that is going in the same direction as n. So therefore, we only want this part of v. And so this goes back to chapter 1. What have I done here? What is this thing here? What does the dot product give me? This is the projection onto n of v. And so we're breaking v up into two pieces. The reason it looks a little different is here we're assuming n is a unit vector, so usually we'd have to divide by the length of n squared, but the length of n is 1, so that just falls off. So we kind of do the usual thing. We only care about the flow that's going through. We don't care about stuff that's going perpendicular to it, for example. And then, no, so yeah, you can see we haven't even gotten to a problem. We might not even get to an actual problem today. And since tomorrow we're doing nothing new, obviously it's not in the test. On the other hand, it will be on the final, so I want to start it today so we can get to it next week, since next week is the last full session. Oh, no, last full week. So this is now the part of the velocity field that we want, so the flow of the water that's actually going through the net. And then to get the actual flow, we would multiply the magnitude of this by the surface area that's going through. So we do the usual integral thing. We'd break our two-dimensional net into lots of little tiny pieces. On a little tiny piece, it's basically flat. And therefore, if we multiply the magnitude of the flow times that area, we're going to get the flow through that little piece over a given time interval. And then we add all up the little pieces. So that's what we want to do. Similar to 4.2, this is going to work nicer if we parameterize. And then something that sort of is on the test. So if R of u gives the surface we want over a region D, so we plug in certain values of u and v, that will give us m. And we know from chapter 1, sort of, that the cross product of the two partial derivatives will be normal to m. And therefore, our n will be this. Because we want it to be a, oops, don't need that at the top. Because we want it to be a unit vector, we're going to divide it by its length. Little thing is this will give us one of the two normal vectors. It could be we really want the other one. So we might have to check that we're getting the right one. If we're not, we'd have to multiply by -1. R view B, oh, this is a M. Okay. So there's the normal vector, and then so we're going to do the projection of V onto this, and then we want to multiply by the surface area. So from 3.11, which is on the test, how do I get the surface area of something if it's parameterized? I'm leaving this here because we'll go into the next one. So how do I get the surface area of something? Of course, it's going to be hard for you to write, but it's the integral of the length of the cross product. So here our normal vector is this. So from 3.11, we know that's the surface area of something. Then you'd have to integrate it. So oops. So if I define this, it's closed, make it look like a gradient. So it's the dot product of V and N ds. If that's the flow through M, then according to what we just wrote, this will be the integral over D, which is the region that gives us our M. Do V. So again, like 4.2, we're going to put in the parameterization into V. And we're going to take the dot product of RU cross RV. And whatever, dy dx or whatever. Or in this case, du dv. So this looks like it's less than it is, but so here we want the length of the dot product of the projection, where we're assuming that onto the normal, which we assume is a unit vector. But so this, which I'll cross out in a second, to make it a unit vector, we should have this. But we have to multiply by the surface area, which is that, and therefore those cancel. And so you can see it's similar in some sense to the 4.2, a bit more complicated. And so we'll do an example after the test. So here we have kind of a similar thing to 4.2 again. So line integrals, we did the base, then we did one simplification and then a second one. In this one, this is going to be the base, which we'll have to do next week. And then there'll be two other sections doing two different ways you can do it. And that's the last thing we do. So obviously we have to do an example, so you can ignore this for now because it's not on the test, but any quick questions on this? Okay. So as I said, the review is on Blackboard. So for tomorrow, what you should be doing is go through the review, check my answers on that are up, and come in tomorrow with questions. So we won't do anything new. Just go over questions you have. So if you remember test 1 review, it'd probably be similar. There'll probably be a couple I'll want to do because they haven't been on a quiz yet. And then I'll ask if you want to do variations of other ones. So any questions about test? Okay, so let me stop recording. And as usual,